Hey everyone, and welcome to this exam prep explainer. If you've got a computer science or physics test coming up on data representation, well, you are in the exact right place. Today, we're going to trace the incredible journey of a sound wave, literally taking it from the physical world right into digital binary code, breaking down absolutely everything you need to know to ace your upcoming exam.
Here's our study roadmap for today. We're going to hit the physics of sound waves, analog to digital conversion, sample rate, bit depth, and quantization, the trade-offs between quality and storage, and wrap it all up with your ultimate cheat sheet.
All right, let's dive right into part one, the physics of sound waves, and what we call the analog problem. So, sound naturally exists as continuous energy, right? It's produced by rapid vibrations, like your vocal cords right now, traveling through a medium like the air around us. To capture this physical wave, you gotta know its two main properties. Actually, I'm modulating my voice right now to show you that a huge amplitude means a really loud volume, and a high frequency means a super high pitch. Basically, frequency is just how often those waves repeat, measured in hertz, while amplitude is the physical height of the wave.
Now here is the fundamental conflict you absolutely need to nail for your exam. We have to somehow translate the continuous, incredibly smooth curve of analog sound into the blocky, discrete, step-by-step language of a computer. Since a computer only understands zeros and ones, it literally can't process a smooth, continuous line. It needs numbers, it needs steps.
Which brings us to part two, analog to digital conversion, or the translation process.
If you only remember one sequential process for your test, make sure it's this exact step-by-step translation. Step 1. Your microphone captures that physical sound wave and turns it into an electrical signal. Step 2. The analog to digital converter, or ADC, steps in to sample that signal. Step 3 is quantization, which is where we round those samples. And finally, step 4. Those rounded values are converted into a neat stream of binary zeros and ones. To really wrap your head around what that ADC is doing during the sampling step, think of it like a rapid-fire camera. It's capturing discrete, frozen snapshots of a continuous moving sound wave. Just like a video is really just a fast series of still images, digital audio is essentially a series of frozen audio snapshots taken at really precise, regular time intervals.
Okay, moving on to part 3, sample rate explained. Basically, how often we measure.
The absolutely crucial definition to lock in here is that sample rate is the number of samples, or measurements, taken per second of a sound wave. The golden rule you need to know? A higher sample rate means you're taking way more of those snapshots every single second. Less data slips through the cracks between measurements, which gives you a much more accurate representation of that original smooth wave. And speaking of sample rate, you're almost guaranteed to see this specific number on your test, 44,100 Hertz. That represents your standard CD quality audio. But why that specific, kind of random-looking number? Well, it all comes down to the Nyquist theorem. This theorem states that our sample rate has to be at least twice the highest frequency we actually want to record. Since human hearing tops out at right around 20,000 Hertz, doubling that gives us 40,000. So 44,100 safely covers the entire range of human hearing with a little room to spare.
All right, part 4, bit depth and quantization. This is all about how precisely we measure.
So, while sample rate is about how often we measure, bit depth is the number of bits used per sample to record the actual amplitude or volume. A higher bit depth gives us a much wider dynamic range. And what does that actually mean for us? It means we have way more digital levels available to use, letting us capture the difference between the quietest little whisper and the absolute loudest shout with crystal clarity. Just to put it in perspective, an 8-bit depth gives you 256 levels of volume, but a 16-bit depth, that gives you over 65,000 different levels.
But here's the catch. Because we're forcing infinite analog possibilities into finite digital boxes, the computer actually has to round those sampled voltages to the nearest whole number. This rounding process is what we call quantization. And here's a pro tip for your exam. This rounding is never perfect. It actually causes a tiny bit of distortion known as quantization error or quantization noise.
Next up, part 5, quality versus storage trade-offs, finding that perfect balance.
You might be wondering, if we want perfect audio, why don't we just crank our quality dials up to infinity? Well, because higher settings process a massive amount of data per second, creating absolutely giant files. That's exactly why a basic phone call uses a really low sample rate and low bit depth to save on bandwidth, while a professional studio recording uses incredibly high rates to capture maximum detail, which of course requires a massive hard drive. So to manage these gigantic file sizes, computer scientists rely on compression. And you'll definitely need to know the difference between lossy and lossless for your test. Lossy compression, like your standard MP3 file, actually permanently throws away some of that audio data to create a tiny file size, so you do sacrifice a little bit of quality. On the flip side, lossless compression, like a FLAC file, shrinks the file down without throwing a single piece of data away. It keeps the audio totally pristine, though the file size is definitely going to be larger than an MP3.
All right, we made it to part 6, the cheat sheet in exam tips summary.
Let's do a quick review of everything we've built up so far. Think of this as a rapid-fire vocabulary check, linking the physical properties of sound right to their digital counterparts. Ready? Amplitude maps to loudness. Frequency maps to pitch. Sampling is the actual act of measuring the sound. Sample rate is how many of those measurements you take per second. Bit depth is how precise those measurements are. And finally, the whole shebang ends up as binary, just zeros and ones. When you finally sit down for that exam, make sure you're ready to confidently explain these core mechanisms. Know the ADC's role in converting electrical signals straight into binary. Remember to apply the Nyquist theorem, just double the highest frequency. Be ready to explain the big trade-off, where higher quality equals larger file sizes. And lastly, know that if your sample rate is just too low, you're going to get a very specific kind of distortion called aliasing, which is where totally incorrect frequencies start showing up in the audio.
I want to leave you with this kind of provocative thought as you head into your exam prep. Digital sound is incredibly advanced, but because it fundamentally relies on discrete samples and rounded quantization, is it ever really perfect? It's always just this beautiful approximation of analog reality, constantly balancing the scientific precision of our measurements against the physical limits of our computer storage. Think about that. Good luck on your test. You're absolutely going to crush it.